Hello everyone. This is the assignment submission for Machine Learning Foundations for Product Managers course in Coursera, module number 6. The context is we will build a model, machine learning model, to predict electrical energy output of a combined cycle power plant. This power plant uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. So we are given a data set. It has 9,568 observations from the sensors of the power plant, which we will use in the model. The data set has columns like temperature, ambient pressure, relative humidity, exhaust vacuum, and net hourly electrical energy output. The fifth column, the PE, the net hourly electrical energy output, is the value we're going to predict. What is expected in this assignment? We are expected to determine the machine learning modeling approach, determine the possible features to use in the model, create a training set and test set to evaluate and compare the performances of different models. So the expectation is that we compare at least two different models, either use different algorithms in the models or same algorithm but use a combination of features or use different hyperparameters. So there must be difference in way you execute the model such a way you can compare and pick the best one. And then finally, when to pick the best one, we would have to have some metrics that would help us pick the best one, and it is explainable. That is the expectations. So model approach. This is a supervised learning problem, machine learning problem. There are two supervised learning algorithms, classification and regression. They both find patterns in data to predict the outcomes, but they differ in goals and output. The classification algorithm categorizes the data points in the data set into a specific predefined groups. Output is a label or a class from a set of options. For example, you train the model in such a way it is able to identify a normal email from a spam email. The regression, on the other hand, the goal is to establish a relationship between two variables, input variable to the output variable. The output is a real valued number that can vary within a range. For example, you can train the weather data set for the model to predict what could be the weather tomorrow. Our problem objective is to predict the net hourly energy output, which is a real valued number, and we are also expected to establish the relationship between the input independent variables in the data set, which is a clear case for linear regression. So our modeling approach would be a linear regression, multiple linear regression to be precise, because we're going to use more than one input variable. Now, let's go ahead and select features to be used in the modeling, right? So what I did is I looked at the correlation matrix. Correlation matrix actually displays the strength and direction of a linear relationship between variables. So on the right side here, you would see this. It's a screenshot. I loaded this data into a pandas data frame. It's a Python library to load a table. It tells us ambient temperature to PE. The correlation is negative 0.94. What it tells us is it's a negative correlation and it is very close to 1, signifying it has a higher strength and the direction, meaning if the temperature increases, the power generation decreases. It has a negative correlation, inverse relationship to be precise. So uh, you can see two of the variables, they show the direction and has a strong strength closer to 1. And pretty much all four independent variables have some strength, but AT and V are more pronounced. All four influence, but AT and V shows would have a larger influence on the power generation output. Okay. Um, what we would do is we would be building a linear regression model, and this is what I'm planning to do. given the ambient temperature and exhaust vacuum having a higher strength and a negative relation, I'm going to use that mandatorily. So the model one, it's the same algorithm, linear, multiple linear regression. We're going to use three columns as features: ambient temperature, exhaust vacuum, and the ambient pressure. The second model execution, which is again the same multiple linear regression, but uses a different set of features: temperature, vacuum, and relative humidity. Finally, we would execute the same multiple linear regression using all four columns as the features. Right, on the right side I have plotted also, just so that you understand what I mean. You can see plotting as the temperature increases on the x, the power generation which is on the y, you can see it is decreasing. Same goes for vacuum, right? The others two are scattered. It had some influence, but it's not that pronounced. So this is going to be our features, and it's going to be a single model algorithm with different sets of features. Okay, now we would have to train our model with some data set, and we have to test the model for its performance using unseen data by the model. So what I'm doing is I'm going to split the given data set into 80% for training and 20% for testing the prediction score. I'm using a Python package called scikit-learn. It has a function called train test split. You give the data x, which is the independent variables, and y, which is the dependent variable, and it's going to split it 80-20, 80 for training and 20 for testing. Right? I've explained in the bottom section of this slide, you could see some explanation on the function itself. It's a utility function provided by this package. It is used to split the data set into two subsets, training set and testing set. The purpose is to train the model using the training set. This involves fitting the model to training data and learning the underlying patterns. The evaluation of the model uses the testing set to evaluate the model's performance on the unseen data. So this helps in assessing how well the model generalizes to a new unseen data. Okay, so I think this is clear for everyone. Move on. So when we evaluate the model, we're going to produce the output metrics, evaluation metrics. We're going to use two: the mean squared error and the R-square. The mean squared error measures how well the model's predicted value matches the actual observed value. For example, if a model is predicting a house price, let's say it's $1 million, actual true value is $1 million. If model predicted 900,000, the difference is 100. So that's the residual or the loss. So we got a lower mean squared error means it's a better accuracy. That is one of the metrics we're going to use to evaluate the model performance. The next one is the R-square. The R-square measures the proportion of variance in the target variable that is explained by the model. Right? The use in the model evaluation, R-square is often used to assess model fit and how well chosen predictors, the independent variables, explain the target variable. It's useful when comparing different models on same data set, especially in the regression analysis. That's what we are doing now. A higher R2 closer to 1 suggests a better model fit where predictors explain large portion of the variance. However, a high R-square does not necessarily mean a better model, as it can also reflect overfitting or a noise, particularly in a complex model with many predictors. This we have seen in the course too. Now, the actual model evaluation, I'm using linear regression, function from scikit-learn. It's basically you create the instance of this linear regression class from, I'm using the scikit-learn library in Python, fitting the model to the training set and making a prediction on the X. I'm going to calculate the mean squared error between the test data and the predicted data. Then also I'm computing the R-square score. I'm also getting the coefficient intercept. Intercept is the beta 0 in the linear equation. This one, the beta 0. So I'm going to get for all three executions and then print in a table, and then we can talk about it. So I executed all three models, you can see model 1 we use 3 features, model 2 different 3 features, and then model 3 uses all 4. Out of all 3, you could see r square closer to 1 is on the model that used all 4 as columns as features, and the mean square average is the lowest among the 3. So the higher r square, model 3 showing a higher r square shows the better fitting to the actual true value, and the lower mean square meaning the better accuracy. So the best model to use is multiple linear regression with all 4 independent variables as features. That's it. Thanks for watching.